So we're going to change gears now. It wasn't a pun because there's a car here. We're changing gears from derivatives to what the second half of this class is going to be about, which is integrals. And we're going to start off with a couple real easy questions to just sort of get us into the feel of what we're thinking about and seeing how these things work. So I'm driving a car. Look at me go. My velocity is 60 miles an hour. And it is a constant 60 miles an hour for, oh, I drew a line there, for these full 2 hours. Huh? How far did I go?
120 miles.
120 miles. Easy enough. Everybody agree with that? No issues there? No, if I went 60 miles an hour exactly for exactly 2 hours, I had to have gone 120 miles. Seems reasonable, I think. All right. What if for the first hour, I went exactly 60 miles an hour. But then for the second hour, I somehow, in my magic automobile, went exactly 70 miles an hour. There was no change from 60 to 70. It was just instantaneous that happened. Okay. How far did I go in those 2 hours?
130 miles.
Right, 60 for the first hour, right? And 70 for the second hour. Should have been exactly 130 miles. Everybody agree?
Yep.
Easy enough. Okay. What if I started at 60 miles an hour and I finished at 70 miles an hour, and somehow I had this magic automobile where I increased at exactly the same rate, at a constant rate over those 2 hours, from exactly 60 to exactly 70. How far did I go? Any guesses?
130.
Anybody agree, disagree with that? What was that?
I agree.
You agree. All right, let's say 130 miles. Anybody? Yeah, I agree. I also agree. Look at that. People agreeing in the chat. That's great. 130 miles. Huh? Yep, you're right. All right, now, those were easy. I hope those were easy. Make it more complicated. Now my car is like a real car. And I started out at 60 miles an hour. Then I got a little faster. Then I saw a bunch of cops, so I slowed way down for a while because the speed limit was only like 40 miles an hour. And I was like, I probably shouldn't be doing 80 when it's a 40 mile an hour zone. Then, cops pulled somebody else over. So I was like, all right, time to start going faster again. And I sped back up. Right? How far did I go? Very far, I suppose, maybe. I don't know. I started at 60 miles an hour, and I don't even know. Let's say maybe I ended at 70. How far did I go?
Would it still be 130? Because it kind of like average out to an average pace, I guess.
I don't know. It might have been 130, but what if my route or my speed was more like this? Like, I mean, I still started at 60 and ended at 70. But this down here was 10 miles an hour because I was driving through, I don't know, traffic through LA or something. So I was only going 10 miles an hour. I don't think that would have to be 130, even though I started at 60 and ended at 70, right? Now my other one looks a little closer, like it might have been maybe around 130. But do we have a good way of knowing?
It's the area under the curve.
It is, but how do I find that area?
The integral.
Oh, okay. Yes, this is true. It should equal the area underneath the curve. That's exactly right. Now, let's go back and look at this one. If this was my curve, right? Straight vertical, or not vertical, horizontal line here at 60. What was the area underneath here?
20, 2 times
60 times 2 should have been 120. What about this one? This one was 60 times 1, right? Oops. And that one was 70 times 1. Good. Everybody agree with that? What about this one? What's the area underneath this curve? It's just trapezoid, right? The base of 60 and another base of 70. Average of the bases times the length, which is 130. Good or no?
Good.
Yeah. Every time it's the area underneath that curve. So how do we find the area underneath this curve of this random function that I don't have an actual function for? Well, I can't find an exact value of it. The best thing I could do is approximate it at this point. So how can I approximate the area underneath this curve?
You can make little slices, like little rectangles under it, and find their individual areas, then add them up.
All right, I'm gonna make some rectangles underneath here. You guys ready? There we go. That's what you said, right? Put some rectangles underneath it. Oh no, it's not a rectangle. Can I find the area of each of these rectangles?
That'll be an interesting approximation.
Yeah, there's a good one. Huh? What do you guys think? Are those? Is that what you? I don't know who was that. Was that you, Yaya, that said that?
Yeah, that was me.
Yeah. You like those rectangles? Is that what you meant?
I mean, they'll work, but not what I meant.
That seems like a lot of work, right? It's like a horrible game of Tetris or something. I don't want to do that. So what did you mean? Now that I'm gonna try to be not a jerk about it.
Like you draw a little like slice from the value of the function at one point down to the t-axis.
Okay. All right,
And
so
then
let's.
you do that over and over for like very skinny blocks that all equal about the height of the function at that point.
Okay. Yeah. So that's going to be our basic idea. Exactly. So in order to find the area underneath this curve, we're going to approximate it using these rectangles that are going to go underneath it, and we're going to do 3 different ways of doing that. One of them is going to be called the left rectangular approximation method. And since I'm really bad at drawing, I've only drawn out 8 different little subintervals on here. So I'm going to have 8 different little rectangles. So I broke down the area from t equals 0 to t equals 1 into 4 different, 15-minute intervals. And same for t equals 1 to t equals 2. So our left rectangular approximation method says break it down into however many subintervals you want, or however many I tell you to break it down into, and go to the left endpoint of the first subinterval. Go to the height of the function and draw a nice little rectangle there. Then go to the second subinterval. So from, this was 0 minutes to 15 minutes, 15 minutes to 30 minutes, and do the same thing. Go to the height of the function there and draw a rectangle. And then do the same thing again. Go to the height of the function and draw a rectangle. And then the next one. And then the next one. And the next one. And the next one. And the last one. And we get this lovely little approximation for the area underneath the curve. Everybody good with that and see where it came from? So what would we need in order to evaluate this? Well, we need to know exactly how fast we were going at the beginning, 60, and exactly how fast we were going after 15 minutes and 30 minutes, 45 minutes, an hour, and so on. Right? We'd have to know those exact data points. We'd multiply them all by 1/4 of an hour to find the area of each one, and then sum them all together. Good or no?
That makes sense.
Oh, good. All right. So we'll note that in some parts of our function, we missed some pieces, true? But also in some other parts of this, we went a little bit over, didn't we? So in some portions of it, our approximation was a little under, and in other portions, our approximation was a little bit over. So those should cancel out a little bit and get us closer and a pretty decent approximation. We might notice that when our function, when f is increasing, what did the left rectangular approximation do? Did it give us an over or an underestimate?
Under.
Should be an underestimate, exactly. And what about when, you guys see the yellow okay? What about when f is decreasing? Our left rectangular approximation is an overestimate. Good or no? So this is a couple of things that you'll want to note because they will ask you about that on the AP test. We'll talk more about it another day, but just make sure you know that. All right, so another way we could do this is by using a right rectangular approximation. So that means instead of using the left endpoints of each subinterval, we use the right endpoint. So we'll start on the right-hand side and draw some rectangles from the right endpoints of each subinterval. And what will we note here? That when f is increasing, the right rectangular approximation is now an overestimate. And vice versa. When f is decreasing, our right rectangular approximation is an underestimate. Everybody good with that or no? Yeah, no, maybe.
Yeah, we're good.
Okay. So if I did a left rectangular approximation and a right rectangular approximation, what do you think the third way that I could do this is? By using a midpoint. Yeah, a little bit tedious here perhaps, but take the midpoint of each interval, find the value of the function there and draw a rectangle. And do it with the next one, find the midpoint, find the value of the function, draw the rectangle. And what do you think about this one? Do you think this will be a better approximation than the other ones or worse?
Probably better because for each point, there's both an underestimate and an overestimate, so they like balance each other out.
Right, exactly. We got a little bit over, a little bit under on each one, whether it's increasing or decreasing, we're a little over and a little under on each one. And so it's a better approximation than both the left and the right. Now, then you're going to wonder, well, why would I ever use the left or why would I ever use a right? Well, there's reasons. It makes a lot of the algebra a lot simpler for a lot of things, and that'd be why. Plus, sometimes a function finding, if I've got an interval from 0 to 1 and finding the midpoints, if there's like 8 subintervals within there, those are some pretty nasty fractions to deal with. Whereas using a left or right one might not give me as many horrible fractions to have to contend with. All right. So here's what we're going to do. We're going to take the function f of x equals x squared, and we're going to see if we can approximate the area underneath the curve from 0 to 3 using a left, a right, and a midpoint rectangular approximation. So what I'm actually going to do here is give us this same thing on 3 different pages so we can do each one separately. So we're going to start with a left rectangular approximation. We're going to use 3 subintervals on the interval 0 to 3. So that should tell us that our first subinterval is from 0 to 1, second one is 1 to 2, and the last one is 2 to 3. Good or no?
Good.
Great. All right, so the first one, 0 to 1, 1 to 2, 2 to 3. The left endpoint of 0 to 1 is at 0. What's the height of our function at 0? Looks like it's 0, doesn't it? All right. So what's the height of this rectangle? Well, it's 0. So really, we don't have a rectangle for that first one. It has a height of 0 and a width of 0. What about the second one? The left endpoint is at 1, which tells us that the height of that rectangle is 1 squared times the width, which is 1. And then the last one here at 2 has a height of 4. So this ought to be 2 squared times the width of 1. And what do we end up with? We end up with 5. And we will note that that is an underestimate because this is a left rectangular approximation. And the function is increasing. So we're missing out on a bunch of chunks of this, right? We're missing out on all this green. Good or no? All right, you guys think you can do the right one on your own? I hope. Take like 30 seconds here and see if you can do the right hand one, and then we'll make sure you did it correctly together. Ready to go. You guys all good with that one? Ready to do it?
Yeah, we're good.
All right, so our first one on the right endpoint should be at 3. pretend that's a really nice rectangle. So 3 squared times 1. The next one should be at 2. So 2 squared times 1. And the last one should be at 1. So 1 squared times 1. And what does that come out to be? 14. And we should recognize that this is way over what it should have been. This is an overestimate. Good or no?
Good.
All right. So let's do the midpoint rectangular approximation. Our subintervals are still the same, 0 to 1, 1 to 2, and 2 to 3, but now we're using midpoints. So the midpoint of 0 and 1 is a half. We should have the length, which is still 1, times 1/2 squared. And the next one should be 3/2 squared times 1. And the last one should be 5/2 squared. And what does that come out to be? A fourth plus 9/4 is 10/4 plus 25/4. That's 35/4, which is what? 8 3/4. And anybody know what the actual value of that is?
8.75.
Well, I mean, of that is 8.75. I meant, sorry, the actual value of the area underneath this curve from 0 to 3. The actual area underneath that curve is exactly 9 units. So with just 3 subintervals using a midpoint, we got off by only 1/4 of a unit, which I'd say is pretty darn good. It's pretty close. Good or no? Any questions or issues there? All right. Let's see if you guys can read through this one and do this one on your own. I'll give you about 2 minutes. Shouldn't take too long. We got an interval from 1 to 9 with 4 subintervals. We want to use a midpoint approximation to find the area under the curve 1/x plus 1. I'll give you about a minute or 2 to do that. Ready to go. Everybody good, or need another second? You guys good, or you need more time?
I think we're good.
All right. Well, if we're going from 1 to 9 with 4 subintervals, those subintervals should be the intervals from 1 to 3, 3 to 5, 5 to 7, and 7 to 9. Everybody would agree with that, I hope. And if we're doing midpoints, our midpoint should be 2, 4, 6, and 8. And what's the length of each subinterval?
Two.
Length of each subinterval ought to be 2, right? So the width of each rectangle that we're drawing is 2 units, and the height is equal to 1 over 2 plus 1, 1 over 4 plus 1, 1 over 6 plus 1, 1 over 8 plus 1. So it ought to be 2 times 1 over 2 plus 1 plus 2 times 1 over 4 plus 1 plus 2 times 1 over 6 plus 1 plus 2 times 1 over 8 plus 1. And what does that come out to be? What was your answer when you simplified that? Anybody?
I got 157 over 12.
157 over 12, I disagree. 121 over 12, I think, sounds better. Yep, 121 over 12, right? 3 halves times 2, so 3. 5 fourths is 5 halves. Right? That one should be 7 thirds. And the last one over there should be 9 fourths. So 9 fourths plus 7 thirds plus 5 halves plus 3. And it comes out to be 121 over 12. Anybody know what the exact value of that is? Not of 121 over 12, but the exact area of the area under that curve. It's the natural log of 9 plus 8. Interestingly enough. Okay, so the exact value ended up being natural log of 9 plus 8 is what that actually is. And if you were to approximate both of these values, you'd find that they're within about 1/10 of a unit of each other. So pretty darn good approximation for the area underneath the curve. And how could we make this approximation better, or any of these approximations that we've done, right, as we've gone through today? How could we make any of these better?
Use more rectangles.
Right, use more rectangles. Right, if instead of using 8 rectangles here, I used 16 rectangles, well, my result would be a lot better. Instead of using 16, I used 100. Well, it'd be a lot of calculations, but it'd be really close to the exact area. And if I used, 1,000 of them, or 10,000, or 1,000,000 of them, I'd be very, very, very close to the exact value of the area underneath that curve. And so that's going to be our goal, is to use as many rectangles as we possibly can so that we can get the best approximation possible. Everybody good there or no? All right, so in order to do that, we need to understand a little bit about sigma notation or summation notation. Everybody good with the left and rectangular and the left rectangular, the right rectangular, and the midpoint rectangular approximations so far? I hope. Yeah, no, maybe. You guys all good or no?
Yes.
All right, so in order to make it so that we can get more subintervals, we need to understand how sigma or summation notation works. And second period, they didn't quite, some people understood and some people didn't. So hopefully you're familiar with the Greek letter sigma. That's sigma, it's a capital sigma. It means the sum of or sum all of these things. So what this is the sum from k equals 1 to n of a sub k. Right? A could be anything. It could be an x sub k, or it could be some function in there. So what this is indicating is it's saying take the first a sub 1, take the second a sub 2, take the third a sub 3, add them together, all the way up until you get to the nth a. So if I said something like this, the sum from k equals 1 to 5 of k, what would that mean?
What do you mean 1 plus 2 plus 3 plus 4 plus 5?
It would mean exactly that. 1 plus 2 plus 3 plus 4 plus 5. Yep. Right. First k is 1, second k is 2, third k, fourth k, fifth k. 1 plus 2 plus 3 plus 4 plus 5. If I said the sum from k equals 1 to 100 of k, that'd be 1 plus 2 plus 3 all the way up to 100. Right? Everybody good with that? What if I said this? Let's make this something simple. 4 k squared. That'd be 1 squared plus 2 squared plus 3 squared plus 4 squared. Everybody good with that? Or no?
Yeah, that makes sense.
All right, cool. So the next thing we need to do with this is we need to figure out then what's the sum from k equals 1 to n of k. Any thoughts on that? What does that mean? That means add together 1 plus 2 plus 3 all the way up to n. So this is just a formula for summing together the first n integers. Anybody know how to do this? Anybody know a formula for this?
First plus last over 2 times how many numbers they are.
Say that again. I heard the second part.
The first number plus the last number divided by 2 times how many numbers they are.
Times how many numbers there are.
Yeah, times. Yeah.
You just said divide by times. Yeah, that's exactly right. And the way we get that is actually fairly ingenious. We could say that this summation should be the same as doing it backwards, right? I can add things in any order, can't I?
Yes.
Well, and if I have one true statement and another true statement, can't I add those two true statements together? That's something you used to do with like solving systems of equations and all that. So each of these, 1 plus n is n plus 1, and n minus 1 plus 2 is n plus 1, and n minus 2 plus 3 is n plus 1, and all of these end up being just a bunch of n plus 1s. And how many n plus 1s do we have? Well, we had n integers, so we ought to have n plus ones. And to get just one summation, we ought to have that divided by 2. Does everybody see how that worked? Or no? Good or not good?
Good.
Okay. All right. There's another one of these that you should also know, which we're not going to prove right now, but you should know that the sum from k equals 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 all over 6. So this is another one you should just know and memorize. Good? Everybody good there? No, both of those. You're not going to have to use them a ton of times, but you will need them for us to evaluate some stuff this unit. Good or no? Okay. All right. We are sort of running out of time. I'm a little concerned if. I think we'll try. We'll try and make it through here. So bear with me for a minute. You don't need to write all this down right now. Just kind of follow along with what I'm doing and what I'm saying in the pictures and all that. And if you want to go back later and write it all down, feel free, because it'll all be in the notes up online. But what I've done here is I've taken some arbitrary function in blue and drawn some rectangles in it. Everybody good and see that I've drawn some rectangles in there? Each of those rectangles comes from the midpoint of each of these subintervals. So there's my interval from x0 to x1, x1 to x2. And somewhere in there, I've chosen an arbitrary rectangle, a random one. It doesn't matter which one. I could have chosen any of them and called it the kth rectangle. So x sub k minus 1 to x sub k with a midpoint of c sub k, right? And this is a generic rectangle that is, I could have chosen any of them. I could have chosen this one or the next one or the last one. It's just supposed to represent any random generic rectangle on this picture. Everybody good with the picture so far? And what it is? It's just an approximation using a midpoint rectangular. Good or no? Okay, I got one good in the chat, so we'll assume that's good. Note that the subintervals are not necessarily all the same length in this case, right? x0 to x1 is probably smaller than x1 to x2. Right? So we've just picked some random subintervals and drawn these rectangles. We could note that sometimes this is below the x-axis, and we talk about below the x-axis. Sometimes we talk about this being a negative value down here. Or it could be above the x-axis, or it could, if I was doing from x3 to this one that I've labeled as x sub k minus 1, it might stretch across. It might end up being 0. It might zero out. And that's fine. So what I want to know is, what's the area of this kth rectangle? First off, what's its height? It should be height times width, right? What's the height of that rectangle?
F of ck.
Yeah, it's f of c sub k, which might look a little bit like how you're feeling about this at the moment. But we got f of c sub k and times our width. What's the width of that? It's the change in the x value of this specific kth subinterval. So I'm going to call that delta x sub k. Would you guys agree that that would be the area of any generic random rectangle if I labeled it as the kth rectangle. It could apply to the first rectangle or the second rectangle or the third or the fourth or the kth. It could apply to any rectangle within there. Yeah? You guys agree or no?
Yes.
Agree.
Okay. How many rectangles do I have? Don't say 3, because that's all that I drew. How many rectangles are there in this picture, theoretically? Here's 1, here's 2, here's 3, and so on and so on, and n minus 1 of them, and now there are n of them,
N.
right? I have n, I'm going to say n rectangles, or n subintervals. So if this formula that I've written represents the area of one of them, couldn't I sum them all from the first one to the nth one? And wouldn't that give me my approximation? Hopefully. Yeah, no, maybe. Everybody okay with that notation? The sum from k equals 1 to n of the area of each rectangle? Good or no? All right, we'll just go on since nobody's answering. I'm assuming that means you're good. This is just an approximation for the area under the curve, right? But it would be nice if we could get more and more rectangles underneath there. Yeah. So we're going to have to find a way to do that. So this summation that we're talking about here is called a Riemann sum. And that's why this whole thing is called Riemann sums. Because this summation, which is the sum from k equals 1 to n of the areas of each rectangle, approximates our area underneath the curve. And if we can make the lengths of the subinterval get smaller and smaller, we should get a better and better approximation. True?
True.
Okay. Now, if I were to go back and look at this real quick and say, which one's the largest subinterval? I don't know. It doesn't really matter. But if I could take the largest subinterval and shrink them all down at the same rate so that that largest subinterval became very close to 0, what would happen to all the other subintervals that were smaller than the one that's almost 0? They would also be very close to 0, wouldn't they be? Yeah. And so we have one subinterval. If we have unequal subinterval lengths, there's going to be one that's larger than the rest. And we call that one this thing called the norm of the partition. And we denote that as double bar with a P. And so if we could make that one approach a length of 0, we would essentially have such tiny little subintervals that would be very close to an exact value underneath that curve. But we can't make the length of this biggest one close to 0 without making all the other ones close to 0, and then having lengths of 0 for all of these subintervals. So how can I get around the fact that I want them to be 0, but they can't actually be 0?
Limit?
A limit. So what we want to do is we want to find the limit as the norm of the partition, the largest subinterval approaches 0, of this sum from k equals 1 to n of the area of each of these rectangles. And if I were to be able to make the biggest one approach 0, all the rest would be approaching 0. And this would end up being the exact value of the area underneath the curve. Now, it's a little bit of a pain at the moment, right? It's got, I mean, I've got it on the next page here. It's got 1, 2, 3, 4, 5 different variables in it. And it's got 5 different variables, plus it's got a limit, plus it's got a summation, plus it's got some function, plus it's got a delta in it. bunch of crap in there, making this very, very difficult to deal with. So what we would like to do, and I'll talk about more of this stuff that's written down here tomorrow, what we would like to do is instead always choose to make the subintervals equal. And if I were to choose to make the subintervals equal, rather than having to make one of them get very close to 0, I could just make the number of subintervals, which is represented by n, I could just let that approach infinity. And if we looked for the limit as n approaches infinity of this same thing, that should also be the exact value of the area under the curve. So we're looking at the limit as the number of subintervals approaches infinity of the sum of the area of all the rectangles underneath that curve. And rather than having a delta x sub k, now we just have a delta x, because if the subintervals are all the same length, there's no specific reason to denote it with a sub k. They're all the same. They're all the length of the subinterval, b minus a, divided by n, which is the number of subintervals. This thing is called the integral, and it is the area, the exact area underneath a curve.